Okay, so in this video, we're going to be going over some properties of the delta function. Delta function properties. Okay, so let me just remind you what the delta function was. So it's this sort of limit. Okay, it's sort of not exactly a limit. I kind of put limited quotes. I'll just leave the quotes off for now. But it's sort of, we can think of it as a limit of these rect functions that get skinnier and skinnier and taller, okay, while always keeping their area equal to 1. So that's what this function's doing. And we're just going to let them get skinnier and taller. I'll just draw the picture real quick. So this is my rect function. Okay, this is 1 over t naught rect of t over t naught. And then we're going to let those get skinnier and taller until eventually it looks like what we draw the delta function as, which is this, just delta of t. Okay, so that's kind of that statement in pictures. And what we want to do now is observe how this delta function interacts with other functions, whether we integrate this delta function, maybe multiply by another function, or just look at this delta function times another function in general. So see what I mean. We want to look at a few different properties of how this delta function interacts in different ways that we're going to be using in the class. Okay, so let's say we're given a signal x of t, and let's just look at what happens if we integrate x of t times delta of t. Okay, this is something that comes up a lot. All right, so we're going to integrate x of t times delta t. Okay, so what is that delta of t? Well, I'm going to write it as the limit. Okay, so it's this limit. T naught goes to 0. Okay, well, the x of t stays the same, and then I'll just plug in what the delta function is. Okay, so I just plugged in for what we've been making this delta function out of, a limit of these rects. Okay, and now what? Now I'm going to rearrange this a little bit. Okay, so I'm going to take the 1 over t naught out. And now what am I going to do to limits? Well, this rect function, see this rect function is 0 unless t is between negative t naught over 2 and t naught over 2. So this function is 0 most of the time. The only time it's not is when t is between negative t naught over 2 and t naught over 2. Okay, in which case that function equals 1 over t naught, but I took that outside, so inside the integral just 1, and all I'm left with is x of t. Okay, so this is the expression I get, and what is this here? So if you think about it, all we're doing is integrating x of t over this range that is with t naught, and then we're dividing by that width. Okay, this is just the average value of x of t over that region, negative t naught over 2 to t naught over 2. We just are kind of adding up all the points x of t in that region, we're integrating them, and then we're dividing by how many points there were, kind of the length of that interval. It's just an average. So this is the average value of x of t over the interval negative t naught over 2 to t naught over 2. Okay, that's what that is. And if I kind of draw a picture of that, let's just say, I don't know, whatever x of t looks like, maybe in that range, it looks something like that. Okay, well, there's x of 0. And as this rectangle gets smaller and smaller, right, what am I really looking at? Well, I'm just going to be averaging the value of this function over this region. And so you can see as the rectangle gets smaller and smaller, that average should look more and more just like x of 0. Okay, so as I limit the region I'm averaging over, eventually that average is just going to look like that point right at 0, that value, x of 0. And so this whole thing just equals x of 0. Okay, so that's kind of interesting that when we integrate x of t times the delta function, it picks out the value when t equals 0. So let me just write that because that's really important. Okay, so this integral, it equals x at the value t equals 0. So what does this integral do? It picks out, as we like to say, the value of x of t at t equals 0. Okay, and what does this also show? This shows what happens if I let x of t equal 1. I let x of t just equal 1, and so I'm just integrating delta of t, okay, well then I'm going to pick out the value of that 1 function when t equals 0. Well, that 1 function is just 1 forever, right? It's just 1 all the time. So what's the value at 0? Well, it's just 1, right? It's just 1. So this is going to pick out the value of that 1 when t equals 0, which is just 1. So it shows that the integral of the delta function is just 1. Okay. Also shows that if I just integrate from, let's say, a to b, this delta function, as long as a and b are on opposite sides of 0, then the same thing's going to apply. I'm just integrating, maybe this is a, maybe this is b, maybe my function here is just 1 between a and b. But still, when I integrate this function times a delta function, it's going to pick out the value at 0, which is still 1. Okay, so essentially all I'm saying is that when we integrate the delta function, we get 1. We just have to make sure that we are integrating across where the delta function lies, right? If this is the delta function, if I'm integrating just from here to here, of course, I'm going to get 0. The delta function's outside that interval. But as long as I'm integrating across the 0 point, maybe that's my a, that's my b, then I'm going to get the integral of the delta, which is just 1. Okay? So good. So those are some good properties. Now, what about a shifted delta function? Okay, what happens then? Okay, what about a shifted delta function? Well, let's see. So we're going to integrate from negative infinity to infinity, x of t, delta of t minus some amount t naught, some shifted delta. And now how can we use what we've done already? Well, what we've done already kind of requires that the thing inside the delta function is our d of that variable. It's the integration variable. What we need inside the delta function is the integration variable. Right now, we don't quite have that, right? Well, what can we do to make this thing inside the delta function be our integration variable? We'll just do a change of variables. Yeah, I think some people call this u substitution. I just call it change of variables. Okay, so we're going to let u be that t minus t naught, and that means that du is just dt. Okay, so what happens when we make that change? Well, our old variable t goes from negative infinity to infinity. So if this variable is going from negative infinity to infinity, all I'm doing here is subtracting some constant. That's not going to affect infinities. So u is still going to go from negative infinity to infinity. Right? When t is negative infinity minus t naught, that's still negative infinity, and same with infinity. Okay? And then x of what? Of t. Well, just bring t naught to the other side. We can see that this is now x of u plus t naught. Okay, that's what t equals, u plus t naught. And we have delta of t minus t naught. Well, that's just u. That's why we did this whole change of variables. And then dt is du. Okay, so this is what we get. Why is this useful? Well, now it's exactly in the form we had above. Now we have some function times delta of our integration variable, and we know that what we get is that function evaluated where the integration variable is 0. So let's do that here. So I'm going to get this function evaluated where the integration variable u, where this delta function is located, right? This delta function is just located right there at u equals 0. Okay? So it's wherever that delta function is located, we're going to evaluate our function multiplying the delta at that point. So we want to evaluate this when u equals 0, in which case we just get x of 0 plus t naught, which of course is just x of t naught. Okay, so what happens here? Well, actually the exact same thing as before. When we have our delta function and we multiply it by some other function x of t and integrate, it picks out the value of that x of t function where this delta function is located, right? Because that delta function is located at t naught, right? It's a shifted delta function. It's located over here at t naught. This is delta of t minus t naught. So all that's happening when we multiply by x of t and integrate is we're going to pick out the value of x at the location of the delta function. Okay, you can always find the location of the delta function by just looking at where this argument equals 0, because that's what delta of t is. It's just a delta function right at 0. So when I shift, I just have to think, when does this argument equal 0? That's where it's going to be located. In this case, it's when t equals t naught. Okay, so let me just summarize that. Okay, so this integral, x of t, delta of t, delta of t minus t naught, okay, dt, this equals x of t naught. Okay, so this entire integral, the entire thing, okay, picks out the value of x where the delta function is located. So just x of t naught. Let me just write that. So this picks out the value of x of t at t equals t naught, i.e., where the delta function is located, right? Because this shifted delta is just located right there at t naught. Okay, so good. And let me just make a note. I think I said this in the previous video, but we plot a delta function. I'm going to just note it here too, with area A as what? Well, let's say we wanted to plot the function A times delta of t minus t naught. Okay, so we know the area of this delta function is just 1. So when I multiply it by A, right, when I multiply it by A, just to do that real quick, I can just bring the A outside. And of course, I'm just going to get A times 1, which is 1. Okay, if I shift, we know that integral of the delta function is 1. If I shift it and still integrate across where it's located, of course, the area is still 1. Oops, A times 1 is A. Okay, so this function has area A. How do we plot that? Well, we're going to put it where it should be located. You can see it's shifted, so it's located at t naught. And we plot the delta function with these 2 bars and an arrow. And then we usually label the height as the area. Okay, so the height is denoted by the area. Because we know the height there is really sort of like infinity. That rect got skinnier and skinnier and taller all the way to infinity. But it's not much use for us to try and plot this with height infinity. Whereas it turns out the area of the delta function is going to play a big role for us. And so we kind of just use the drawing, use the height in the drawing to denote the area, in this case, A. Okay. All right, great. So this tells us how to work with delta functions and when we multiply other functions by them and integrate. So what happens when we just multiply a function x of t by a shifted delta function, delta of t minus t naught? Okay, so what happens if we just multiply? Let's see what happens then. Let's think about it. So let's say I have some function, who knows what it looks like. Maybe this is my x of t. Okay, and let's say I label some point t naught. And so the value of x of t there is just x of t naught. And what happens if I multiply that by a delta function at that t naught location? So this is delta of t minus t naught. Okay, what happens when I multiply them? Okay, what am I going to get? Well, definitely when I multiply this delta, it's 0 almost everywhere. Okay, so definitely this function should be 0 almost everywhere. The only place where we're not sure what happens is right at t naught. Okay, but definitely everywhere else, this function should be 0 because this delta function is 0 everywhere. Okay, so what happens at that t naught point? Well, one way you can kind of think about it is think what happens when this delta function isn't quite a delta function? What happens when it's just a rect function? And in that case, Okay, what we're going to get is that rect function times this x of t function. Okay, so I just kind of took out that snippet of x of t naught nearby it, right? Nearby x of t naught, just kind of drew the function there. And so this is approximately equal to what? Well, as this rectangle gets smaller and smaller, you can kind of think of this line as approximated just by the value of x of t at that middle point, okay, which is x of t naught. So this is approximately x of t naught times that skinny tall rect. Right? And so as that rect function gets skinnier and skinnier, its height is going to look more and more just like this x of t naught value. Okay, and in the end of the day, when we take that limit, this thing's going to go to delta, and it's just going to be delta multiplied by that x value at t naught. Right? All I'm saying is that we're taking this delta and we just want to multiply it by that value x of t naught at the location where the delta function is sitting on the t-axis. Okay, and this is sort of the argument why. Yeah. Because at any point, we're going to have this rect function. It's going to multiply this x of t function. But as the rect gets skinnier and skinnier, okay, it's just going to look more like a flat line where the height of that flat line is going to be about x of t naught, the value right there in the middle of the rect function. Okay, so at the end of the day, what we get is just going to be another delta function located at t naught, but now the height, in other words, the area, is going to be given by the value of x at that point, t naught. Okay, so this is x of t naught, delta of t minus t naught. And so let me just summarize this. Okay, so what I'm saying is that if I take a function and I multiply it by a shifted delta, what's going to happen? Well, I'm definitely going to get that shifted delta. Okay, the only question is, what has the area been scaled by? And all I'm saying is that the area gets scaled by the value of x at that location the delta function is sitting in. So x of t naught. Okay, so x of t times delta of t minus t naught, you just get a delta function whose area is scaled by the value of x at the location of the delta function, which is t naught. Okay, and let's just check. This also shows, okay, let's check that other property using this. I have the integral of x of t times delta of t minus t naught, dt. Okay, this is what we saw above. We know that this picks out the value of x of t at the location of the delta, so x of t naught. But now we can actually use the property we just talked about to say, oh, this inside function is really just x of t naught times delta of t minus t naught. Now the x of t naught I can bring outside the integral, and I get delta of t minus t naught. And we know that this thing, it's shifted delta just as area 1. And so I just get x of t naught just like before. Okay, so this integral, when I integrate x of t times a shifted delta, it picks out the value of x of t at the location of the delta function. Okay, so these are some properties we're going to be using throughout the rest of the class of the delta function. So hopefully they all make sense and you'll kind of see how to use them as we see more examples. Okay, well, that's all I have for this video. I will see you in the next one.